Hey there, this is Math 7, Unit 2, Lesson 7, Comparing Relationships with Tables. So we're going to be looking at a variety of relationships and how they work together, maybe with things like scale factors and rates and stuff like that, but in a table format, so like so. So here we go. Number one, first thing you did in class today was adjusting a recipe, and it said that a recipe calls for the juice of 5 lemons, 2 cups of water, and 2 tablespoons of honey. Or if you were to have that in a chart, you might have a table, you might have something like a lemon, water, and honey. Is kind of how this one is set up like that. And we had 5 lemons, 2 cups of water, and 2 tablespoons of honey. So that's what our initial table would look like. If we were going to create 4 new versions of that, and we wanted one that had more lemonade, so the overall what we're making, but tastes the same as the original, if we're going to have the same exact formula and have more of it, we could do something like a scale factor of 2, which would mean I take each of those values, 5, 2, and 2, and multiply them by the scale factor to come up with a greater amount of the lemonade, which would be 10, 4, and 4. You could pick any scale factor you want. As long as you apply that through every one of the ingredients, you're going to have the same great taste and just more of it. If I wanted to make less lemonade but the same taste, then I would use a scale factor that would be less than 1. So I could use something like a half, right? And cut everything in half. So if that's the case, I take my 5, my 2, and my 2, and I multiply them by a half, multiply them by a half, multiply them by a half. I know it's not set up as nice as we might want to see it, but 5 times a half, or 5 over 2, becomes 2.5. 2 times a half, and here it is right here, 2 times a half becomes 2 over 2, which is 1, and that one is 1 as well. So my formula to make the same tasting lemonade, but less of it, could be something like 2.5 to 1 to 1. If I wanted to have a stronger lemon taste, then that's going to mean I need to increase the amount of lemons that I'm using. That number needs to go up. And you can pick any number that you wanted to. So we initially had 5, 2, and 2. I could pick 8 lemons for 2 cups of water, 2 tablespoons of honey. Okay, as long as this number is increasing and greater than 5, then you're going to be okay. If I want one that had a weaker lemon taste, now I want to take the lemon value down. So I want a value that's less than 5. So I could say 3 lemons and 2 and 2. Again, as long as that is less, you're in the right ballpark. The next activity was about visiting the state park. And it was talking about going to a park and how much it costs per vehicle and per person in the vehicle. And you used a little problem here that said, okay, it costs $6 per vehicle. There's my cute little vehicle there. And every person inside the vehicle is going to cost $2. Okay? So this is going to be something that every car pays for, but every time you add a person, you're adding $2 more to your bill. But at the same time, that means that it's going to be decreasing the overall cost per person. Let's take a look at this. It says, how much would it cost for a car with 2 people to enter the park, 4 people, 10 people? Record your answers. So first of all, let's keep in mind that the rate per person, right, is times 2. So every person that comes is going to cost $2. $2, $2. So that's going to be how much my person cost will be, is that times 2. But every person is driving a car, so I'm also going to add the $6 vehicle fee to each one of those situations. So 2 times 2 is $4. That's the price for the people, plus the $6 for the car gives me 10. 4 times 2, because 4 people times $2 a ticket is 8, plus the car gives me 14. And then 10 people times $2 a ticket gives me 20, plus the car gives me 26. All right? So for each row in the table, if each person in the vehicle splits the interest cost equally, how much will each person pay? So the idea here is, well, if I take the 10 and I divide it by the number of people, 2. Divide it by the number of people, 4. Divide it by the number of people, 10. Right? I do this, then I end up with 5. I end up with $3.50. This is money, so I can put it in money terms. I end up with $2.60. what we can see is that these values are not the same, right? These are all different values, 5, 350, 260. I can see that the more people I add, 10, the less per person someone has to pay. Okay? So I fill my car with a zillion people, it's going to cost less per person. How might you determine the interest cost for a bus with 50 people? If you were going to do 50 people, you would take your number of people, 50. We would multiply that by the $2 fee. We would add the $6 price for the car, and that would give you your cost. In this case here, 50 times 2 is 100 plus 6 is 106. Okay? 106 people are fitting inside of that car. And just for kicks, if you got 50 people in that car, and you divided that price, now it's going to cost a total of $2.12 for you all to go if you were to take the price and divide it up evenly. Okay? So that would be a division part. So that's just like an extra, you don't have to worry about that. Is the relationship between the number of people and the total interest cost a proportional relationship? Explain how you know. And again, it's something you talked about in class. We would say no, it's not. And the reason it's not is when you look here, these kind of x over y values dividing 10 over 2 does not give you that same rate, the same proportion. There's not a constant proportionality there. And the reason for that is that while this part is staying constant, because we have this vehicle fee of 6, it throws everything off. Because that's actually the value that's being reduced every time you add a person in the overall thing. Okay. What equation could you use to find the total insurance costs for a vehicle with any number of people? So we're talking about if I have people, okay, if I have some people, we don't know, call them P, I'm going to multiply the number of people by $2, all right, so $2. I'm going to add the $6 vehicle cost, and that would be my total cost, the total insurance cost. So something like that. So you could have P times 2 plus 6 equals C, or I could write this the other way and say it's C equals 2P plus 6. These are the same things, just written opposite way, depends on which way you want to read that problem out. Okay. The next activity did was on running laps, and it says that two kids, Han and Claire, were running laps around a track. The coach recorded their times at the ends of laps 2, 4, 6, and 8. Okay, 2, 4, 6, and 8, and then we want to complete the chart here. The first question says, is Han running at a constant pace? Is Claire? How do you know? Well, let's find out their minutes per lap, or in a sense their constant proportionality. To do that, we can take the second value, if we have xy, and we divide by the first, so 4 over 2 is the same as 2. 9 over 4 is the same as 2 and 1/4. Right, I could write 2 and 1/4, or I could write 2.25. That's fine as well. 15 over 6 is the same as 2 and 1/2 when I reduce that, so 2.5. And then 23 over 8, it reduces to 3 and 5/6 there. Okay? When I look at Claire, for Claire's information, we have a 5 over 2, which is 2 and 1/2. We have a 10 over 4, which is 2 and 1/2. We have 15 over 6, which is 2 and 1/2. And we have 20 over 8, which is also 2 and 1/2. So, is he running at a constant pace? We would probably say for Han, nope, it's not. And the reason is that our constant proportionality is changing every time he's being measured, whether it be 2 minutes or up to 3 and a bit more minutes per lap. Is Claire's pace a constant? Her pace looks like a constant, but we could probably say it's a maybe, it's kind of a most likely. And the reason for that is that while this stays the same, 2.5 or 2 and 1/2, that's the same. That's also what her time is when she completes that lap. She's gone around one time, and then she's gone around a second time. And we know that by the time she gets here, it's definitely taking 2.5 minutes to get from there to there. Okay, we can say that's for sure. We know that. But maybe the way she's running is that sometimes she'll take a lap and she'll sprint the whole thing, and then when she gets here, she just kind of walks out the rest and goes slow. Maybe then after she walks slow, she starts off the next one slow, and then goes, oh, I better hurry up, and then she speeds up. So without watching her run, we don't know for sure, but most likely we could say it seems to be, based upon the table information, a constant rate, but it's hard to verify that unless we're watching Claire run. Write an equation for the relationship between distance and time for anyone who is running at a constant pace. All right, so to do this, we would look at our x and our y values, and so we have the formula we've used before is the y equals the constant proportionality times the x value. And in our case here, we could say y is our time, so we can say time equals our rate. So in this case here, we could say for her it was 2.5, and that would be times the distance. Okay, so we could say t equals 2.5 d, and that's one way we can look at that there. Okay, can you write it a different way? Sure you can. You can write it a different way because we've always said that there are reciprocal k values of constant proportionality. So if we used to have like a 2, we would say the reciprocal of that is 1 over 2. So in this case here, because my constant proportionality is 5 over 2, I could also write that as a 2 over 5 value, but I have to change my variables around just a bit. Okay, if I did the 2 over 5, if you did this one here, that would be going distance, right? Distance over time. So if I'm doing distance over time, if that was something else I was going to look at, if I did distance over time as my 2 over 5, then the number I want to put here is going to be the time, so that the time terms here cancel out, and I'm left with just the distance for my solution. So I could have another one where d equals 2 over 5t. That could also be a solution because it is reciprocal, right? But just depends on how you look at it. For what we have here in our x and y table, we would set it up this way with t equals 2.5 or t equals 5 over 2d. Alright, so that's how you can look 2 ways. So this is a little bit of the tricky part when you look at this stuff, because it does matter how you set things up, and it does matter which terms you're trying to eliminate here in this section with that constant. Let's take a look at the summary. So for a summary, we would say that they give you two examples here of smoothie shop, and what you see is that in terms of the dollars per ounce, as our x, our y, and our k, this seems to stay a constant no matter what size smoothie you're getting. Or over here, with our x and our y and our k value, the dollars per ounce seems to change, doesn't it? So you can get a kind of a greater value the larger your smoothie is going to be. And so when we look at that, we just need to say that in these situations, there could be a proportional relationship between the smoothie size and the price. That's what you're talking about there. If there's a proportional relationship, then you can define that as, in this case here, 0.75, which is what we see in this place here. In general, two quantities in proportional relationships will always have the same quotient. That's that y over x value, that quotient there. And then if we know the relationship can be represented by an equation is in the form y equals kx, then we're sure it's proportional. So if you can write that down in a way that shows that it is in the y equals kx formula like this, then we can say that it is proportional. Let's take a look at tonight's homework.